Okay, as you're looking at these problems, these here are some keywords. So compounded quarterly is very different than compounded continuously. Compounded continuously, you're going to use the formula PE to the RT. Compounded quarterly means you're going to use this formula here. So it's very different in terms of what it is that you plug in. Let's go ahead and look at this one first, since it is first. P is the principal, whatever it is that you started with. So our principal is this number here. R is the rate, the yearly annual interest rate, but that's as a percent, and we can't plug in a percent. We need to write that as a decimal. So you move the decimal point 2 places to go from percent, which is out of cent, like 100. You move it over, which becomes 0.012. N is the number of times compounded per year. So if it says quarterly, that means 4 times a year. If it says monthly, that's 12 times a year, so whatever that is. So in this case, it's 4. This is the same 4 that goes up here. And T is the time in years, which is 8 in this case. So this is what I need to plug in. So this is telling you how many times you're going to multiply this, which means 8 years, 4 times a year, so a total of 32 times. And this here is 1 plus the percent, but we're splitting up that percent into 4 tiny little bits. So when we're plugging this into our calculator, so you can see this, we have our 17560, so that's our beginning part. 1 plus 0.012 divided by, 4. And then I want to have that all to that. And mine here is actually showing up at the top there. I actually am going to just make my life easier and write 32, because 4 times 8 is 32. Sometimes it doesn't show it up there, and you would have to put the 4 times 8 in parentheses, all of that in parentheses, but we're all up on top there, so it looks good. So that's it. You would just go ahead and plug all that in. You have $19326.55. So PERT is different. E is a number. It's 2.7-ish. So we would still have our principal. So here's our principal. E is actually a number, but we're going to use that on our calculator as E. And then again, we've got rate. So R stands for rate, just like this, but rate as a decimal. So that means 0.047. We don't need to worry about the 1 plus or anything like that. And then 30 years is our time. So we're going to plug this in, 629000. I'm going to do E. And I use the button closer to the LN down here that has E to the power, because I know I wanted to be in a power anyhow. You can use the other one too, you just have to make it into a power. And then we want times 30. So I want to make sure that all of it is still up there. If yours comes down, you need to make sure you put parentheses in there. Whew, that's a big number. So we have 2576355. So $2 million. Whew, that's an expensive house. 4. So that would be our cost there. Okay, so that is dealing with compounded. Now let's go ahead and work with graphing exponential. So graphing an exponential, we want to, well, let's go ahead and talk about how this transforms into this one here. So this one here was not up at all, and now it is up. So I would write +3. This one was at -2, and now it's at -1, so we're going to move it over 1 to kind of get to that spot. So again, from here to here, we went up 3. From here to here, we went over 1. Now, what we're going to do is we're going to graph this little guy. So the first thing that I'm going to do is I'm going to graph it as though it didn't have any of that. So I am going to graph plugging in 0, which makes this a 1, and then a 3. I'm going to graph plugging in 1, which is up here at 12, 1, 12. And I'm going to plug in -1, which makes that 3 over 4. Remember, a negative exponent flips it, which puts us basically right about there. Now, I'm going to move those things. So now I'm going to go from here up 3, to the new one, my new one, and my new one. And I'm also going to go to the right one. So I'm going to go here, and here, and here. And that is what is going to be graphed. So some things come out in here. One, it's never going to go lower than this. These are my y values that are never going to get down there, so my range is just above 3. This is my asymptote. It ends right here, meaning my y values. My y's end at 3. My domain are all the things that you can plug in. In an exponential, you can always plug in whatever. No matter what it changes and transforms, you can always plug in a number and it will generate a value. But the outputs are limited and they kind of end at this little spot here. Now that is completely opposite of logarithms. Logarithms is the inverse. So if here the domain is everything, here the range is everything. If here the asymptote is a y equals, here the asymptote is going to be an x equals. So the x equals for this one here, when I graph this moves it to the left 5. So at x equals -5, I'm going to have an asymptote. If I plug in a -5 here, I would get 0. Can't do that. If I do log of 0, and I'll even show you, if you do log of 0, it says, no, arrow domain, you're not allowed to do that. If I plugged in a negative here, so like log of -1, log of -1, same thing, it says no, you can't do that. So what we find is that this is my asymptote here, and the asymptote is about the x's, and so it's the domain that's going to be limited, and it's going to be all the x's that are greater than -5. Because if I put in -4 here, I would get log of 1. Well, you can totally do, you can totally do log of 1. That's no problem. It will be fine there. So where our domain is limited on our logs, our range is limited on our exponentials, and these are inverses of each other, so that's exactly how it should be. Right here, when you get these, the first thing I would do is just identify what things you're talking about. These guys here both have these kinds of asymptotes. They're going up and down. You guys have seen those for ages. Those are your exponentials. These guys here are the weird guys. They are the asymptotes that go up and down. These are your logarithms. These are new. You haven't seen these quite as often. So here we're saying which ones will have an asymptote of y equals 0. In other words, right here. If it had asked for the asymptote where x equals 0, it would be our logs. Just like these are x equals, these are y equals. So if you've done it here, you should be able to approach it here as well. The graphs that could be inverses of each other are not these two. This is an increase and a decrease. That does not mean inverse. Inverse means the x's and the y's have switched. This is an increasing exponential and a decreasing exponential. As you can see, this is going up. This is an increasing log, and this is a decreasing log. So if I have y is equal 3 to the x, that is an increasing exponential. If I switch the x and the y, and then solve for y, I have to write this as a log. So log base 3 of x is equal to y. This is the inverse of this. This is increasing, and this is also increasing. These are inverses of each other. These are inverses of each other. You have to have like a normal number. If this was 1/3, this would also be 1/3. So in terms of our inverses, these are both increasing, but one is an exponential and one is a log. So A and C are inverses of each other. This is an exponential, this is a log. They're both decreasing. So B and D would be inverses of each other. Again, going up and going down does not mean inverse. Inverse specifically means changing the x and the y. All right, this one here is a log of something less than 1, so it is going to be decreasing. So this here, letter D, would be the one that is decreasing. Last but not least, we're trying to figure out which one is an increasing exponential function. Not those. These are our exponentials. This is literally going up, which is a. This is going up. That would be our increasing function.